So we continue with our look at the definite integral with section 5.2, and we'll see this familiar limit here from the previous section. And this is the expanded form. This is the condensed form using the summation notation, right? So we've got this limit, this n approaches infinity, and then we've got this sum here. We'll see this is called a Riemann sum. But basically we're just taking each one of these is a rectangle. So we've got the height of the rectangle, right? The function evaluated at the x coordinate, which will give you the y coordinate, or the height times delta x. So this is an area of a rectangle, and we sum them. And if we were to do that with 100 rectangles, then 1,000 and 1,000,000, we use the limit to find the limiting value. So the limiting value would give us the value that if it were possible to divide a region under a curve into an infinite number of infinitely thin rectangles, and if we could somehow add those up, we would get the value that we'd get when we take the limit. So we're taking the limiting value of these. If we divide these into more and more rectangles and add up the areas, that we're going to use a limit to determine what that value would actually be. So we found an example where this ends up being the distance traveled by an object, but you will see, especially in Calc 2, when you really get into a lot of the applications, that this type of limit occurs in all kinds of places. So it'll come up when you find lengths of curves, volumes of solids, centers of mass. A lot of the formulas for geometric objects in 3 dimensions, where you have the surface area of a sphere or the volume of a sphere, those formulas come from calculus, and you'll be able to determine those formulas for like the general formulas for these objects when you're taking calculus 2. So you'll see these formulas for volumes of solids. You'll also see where this comes up for centers of mass, force, work, velocity, displacement, and a lot of other things. So because of this, we give this limit a special name and notation. And it which I probably mentioned before, is this is a really difficult way to do integrals. So when we get into the next section, 5.3, we're going to look at the fundamental theorem of calculus, which will free us from this. This is a really difficult way to do this. We're going to come up with an easier way, but the heart of integration is this limit definition. So we have to study it. In section 5.1 and 5.2 do exactly that. We study it. They're very tedious sections because we're going to just continuously add up these areas of rectangles. So we'll continue with that in 5.2. So we're going to look a little closer at this area under the curve, and this will be fairly familiar because we did the same thing in 5.1. So we're going to divide up this area under the curve into these little rectangles. So we do the same thing as before, this A. So we're interested in an area underneath this function between A and B. We want to find the area under the curve between A and B. So we call A x sub 0. We call B x sub n, just like before. And we find x sub 1, 2, 3, etc. by starting with A and adding delta x. And then this is just a typical rectangle, which we'll talk about in a second. So we're going to use the sample point somewhere in here to get the height. So it looks like it's the midpoint. As long as we take the limit, it doesn't matter which point we take here. We'll get the same area as long as we take the limit. So just imagine you have some rectangle and you use something like, in this case, maybe the midpoint to get the height of the rectangle. Then you go straight across. So we'd find the area of this rectangle here. So suppose this function is continuous. So there's no jumps, there's no holes. It's a continuous function defined on closed interval AB. So we're going to divide this interval a, b into n subintervals of equal width. So they're going to be equal width. So delta x is just going to be b minus a, which gives us the distance from here to here. Right? B minus a gives us this distance, the length of the interval from a to b. We divide it into n pieces. There's going to be n rectangles, so that delta x, each one of these rectangles would have a width of delta x, which is b minus a over n. And then we let these points be the endpoints of these subintervals, right? So each one of these little rectangle bases is a subinterval. And we let these x sub 1 star, x sub 2 star, etc. These are going to be any sample points in these subintervals. So it's just a sample point. We use that sample point to get the height of the function at that point, right? So we'd use sample points like for, let's say for this first rectangle, we could use a left end point here and use this to get the height, right? Should be an overestimate. Or we could use the right end point here, so we get the left end point or the right end point. If we use a right end point and come up here, we'll get an underestimate. Or we could use the midpoint, right, and there'd be probably a better estimate than either the left or the right. And then the sample point could really be any point in between here. So that's all that's saying. Just pick some point in here to get the height. So then x sub I would lie in the ith subinterval, right? So x, look at like, well, here's, I guess, a good picture of it. So we're just going to have this x sub I star is going to be in here somewhere. So the definite integral from a to b is this. So we've got this definite integral. Definite integral. Well, we've got this new look here. So this definite integral, which basically this is the definite integral from a to b of f of x dx, is equal to this. It's equal to this limit of these Riemann sums. So we're getting away from this notation and going into this notation. And this will be true as long as this limit exists. I've mentioned this Riemann sum a few times. Riemann sum is just this sum of these rectangles. So when we talk about the area under the curve and when we get the exact value, we take a limit of these Riemann sums. This is just named after a mathematician who, when all the ideas were being put together, he was one of the mathematicians right in the mix figuring all this out. So there was a time when Newton and Leibniz were using calculus, and it didn't really have the rigor. It worked. People could see that it was working, but there was still some criticism because it didn't have the rigorous background that some mathematicians would have liked. So in the next 100 years or so, a lot of people put all the foundations in place, and he was one of the mathematicians who worked on that. So this is named after him. But a Riemann sum is just a sum of these areas, right? This is the height of a rectangle. This is the width of a rectangle. So you have length times width. So when I mention Riemann sum, that's all it is. It's just a sum. It's a sum here, right, of these areas that are computed from the rectangles. But I wanted to show you about if you look at this notation here, it kind of makes sense if you think of what's happening here. So we are going to take basically, I guess you could think of we're finding the area under this curve. Here's this function f of x, at least a piece of it between a and b, and we want to find the area underneath here. So to find this area underneath this curve from a to b, what we do is we take a really skinny rectangle like this rectangle right here. We're going to think of this really skinny rectangle, so thin that the width of it is just dx. And then the height, if you want to find the height of this, wouldn't you just put whatever this x coordinate is, put it into the function, so you get f of x? So we basically have a rectangle. We know the area of a rectangle is just a length times width. So in our picture, it would be f of x times dx, right? Here's dx, that's the width, or however you want to call it, length times width or base times height, however you want to define a rectangle. It's one dimension times the other dimension. So in this case, if this is the width and this height here is just f of x, the area of this really skinny rectangle is f of x dx. And so that's where you, with the notation, you see it right here, f of x dx. So you would sum, you take the sum, right, the sum of all these really skinny rectangles, and you'll get basically the sum of all of these areas. So this little s here, Leibniz used this because it looked like an S. It looks kind of like an S. And the S is to think of sum, like the word sum starts with an S. So just to make note of this notation, we can see from the picture it looks like it's the sum, right, like an S. It's the sum of all of these areas, length times width, right, these infinitely thin areas. Because once you have this notation, that means you've taken the limit. You've taken the limit. And also one thing you notice in math in general, when you see delta x, it means a change in x. When you see dx, it means a change in x, but after the limit has been taken. So it's sort of like an infinitesimal change. It's a change in x, but you've taken the limit. So it's like the limiting value as x gets infinitely small. So you just notice this in math. Delta x means there's been no limit taken. Dx means you've taken the limit. So remember, these are equivalent. The limit of these Riemann sums is how we're going to define this integral. We're defining this integral as a limit of the Riemann sums. So here we'll see a couple other things we should make note of. So x, that is the variable of integration. And in Calc 1 and in Calc 2, you'll have one variable of integration. In Calc 3, when you study multivariable calculus, you could have more than one variable here. You could have dx, dy, dx, dy, dz for triple integrals. But for Calc 1 and Calc 2, we're going to have one variable of integration. And this is the integrand. It's a word that we will hardly ever use, or maybe never, but technically this is called the integrand. And it is the function that we integrate. And this is called the upper limit of integration. And this other one, can you guess what this one would be called? The lower limit of integration. Okay, what else do we have? This is, of course, the integral sign. It's meant to look like an elongated S from Leibniz. And, okay, I think that's probably all we need to kind of see where this stuff comes from. I will make one more note. I'm going to put this in red because this is it's kind of like a rookie mistake that you don't want to make. When you see this symbol, we need to see this symbol. Okay, these always go together. These two symbols are always together. It's like eating a peanut butter and jelly sandwich without the jelly. Just does not happen, right? These two have to be together. So as you're working on these problems, after we integrate, this symbol will go away, then this goes away too. So you don't want this without that. You don't want this without that. They're both there or neither is there. So just kind of keep that in mind. So you got this midpoint rule, and we'll use this to get an estimate of an area under the curve. or in other words, the estimate of a definite integral. So we can recall here that the exact area of a region that lies under the graph of a continuous function f of x equals, now the reason it's an exact area is because we're taking the limit, right? The area equals exactly, not approximately, exactly the limit of the right-hand sums as n approaches infinity, or the limit of the left-hand sums as n approaches infinity. Because remember, if you take the limit, then you're going to get the exact answer, and it doesn't matter which way you go, you get the same answer. And then, of course, this is another way to say these same things, but with any random point, a sample point, right? So where this would always be the right-hand endpoint, this is always the left-hand endpoint. This is saying you can pick it to be any point at all. Left endpoint, right endpoint, random point, any point inside each rectangle you can use to find the height. Remember, this is just a formula for a rectangle, base times height, right? Here's the height, here's the base. Then there's another one that we didn't talk about, but it also holds true, and that is the limit as n approaches infinity of m sub n. So this is just saying the midpoint, right? Right endpoint, left endpoint, any point, midpoint. And that's when we're going to look at the midpoint rule, because typically what we'll find out is if you're not taking the limit, if you're just going to get an approximation, because sometimes we're going to see these limits are not easy to deal with sometimes. So if you're not going to get the exact area, but you're going to get an approximation, very often this is going to be the better one, the more accurate one, more accurate than these two. But we'll see that in a second. So with our new name, and our new name is definite integral, sometimes you may have, or some of you may have heard the expression indefinite integral. We'll see that in 5.4 we'll make that distinction. But a definite integral means that these endpoints are here, a and b are here. Indefinite integral is when a and b are not there. But with our new name and notation, instead of using these limits, we can say the area equals exactly this, right? Not approximately, exactly. So this integral will give us the area underneath this curve. If you graph this function, the area underneath that curve between a and b can be found by integrating this function. So it's convenient to use left or right endpoints when computing the limit, resulting in the exact area. Remember, if we're going to take the limit, we're getting the exact area. So the exact value of the integral. But if you want to find an approximation, so an approximation, this means when we do this, we are not taking the limit. And you might say, why would you get an approximation if you can get the exact area? Well, we're going to find out that sometimes these limits can be an absolute nightmare. So sometimes the best you can do is get an approximation, right? So sometimes you might set this up, you try to take the limit, and you're like, there's no easy way to take that limit. So there is often an easy way to get an approximation. And you can make it as accurate as you want, as long as you're willing to put in a little bit more work. So we're going to take a look at this midpoint rule. But to get started, I've got this really wide rectangle here. So it's kind of like a wide interval. And just to show the difference here. So if you were going to find the area underneath this curve, so here's our curve. We're going to approximate the area. If we use the left-hand endpoint, we would come up here, we'd have this little rectangle right here, right? So we're going to be missing a lot of we're going to be way under. Now if we use a right-hand endpoint, we come up here, we're going to use this big rectangle, so we're going to be a little bit too high, right? It's going to be too big. So if we use the midpoint, we'd come up here, we'd hit at this point. At that point, we go with the height. So you can see that this shaded area here, where 2 is an overestimate using our rectangle, and this here is an underestimate. So with the midpoint, these two tend to somewhat cancel each other out. Not perfectly, but they help to cancel each other out, where if the left endpoint and the right endpoint, generally speaking, doesn't work as well. So this midpoint rule that we look at, and you'll look at it again in Calc 2, it gives us a way to approximate areas under the curve, which is typically a pretty decent approximation because of this effect that happens with a lot of the rectangles. Not all of them, because this curve will be shaped differently, but generally speaking, it works out for us. So to look at the midpoint rule, we've got this right here. We're going to try to we're trying to estimate this integral. Remember, this integral can be interpreted as the area under the curve, right? So if we want to know really exactly the integral here, the definite integral, the exact value of this, it's the same as the exact area under the curve. So this means that we're not going to get the area exactly because there's no limit here, right? We're basically going to add up a bunch of areas of rectangles, right? We've got this Riemann sum, n of them. So if we use 4, if we go from 1 to 4, we're going to get an approximation. If we go from 1 to 400, we're going to get a better approximation because the rectangles will be really thin and the errors will be really small. So the higher n is, the better this will be. But of course the trade-off is there's more calculations then. Not as big of a trade-off now because we have calculators and computers. We can make programs to do this, so not a huge trade-off like it used to be. But see, this is just the expanded version of this. So delta x times all of these y coordinates, which is the sums. And this is how we did in 5.1 also, right? Because basically if you expand this, you plug a 1 in here, and you get f of x sub 1 bar times delta x plus, then this goes to 2, f of x sub 2 bar delta x. So they'd all have a delta x, you factor out the delta x and you get this. The only thing we haven't seen yet is this bar. And this bar is just, it means that it's the midpoint. So it's the midpoint of these two numbers. So this would be like x sub 4 comma x sub 5, right? So this is just the midpoint formula from geometry. You add up those two numbers and divide by 2, which is the same as adding them up and multiplying by 1/2. So when you see this bar, it just means the midpoint. So you're finding the number, you're finding the height of the rectangle by using the number right in between these two endpoints, right? So if you look at our picture we had before, so here would be, like, let's say this is x sub 4 and this is x sub 5. This is the number right in between those two. So you use this number to get the height of the rectangle, right? This is the one you use, the midpoint, the point right in the middle. So we use that, and then delta x is the same as before, right? B minus a over n. So let's just try this formula out and see what we can do. But first I'm going to show you how to do this on the calculator. So the calculator can handle, the TI-83 and 84 can handle definite integrals. So as long as it's a definite integral, we have the numbers here, our TI-83 and 84 can handle it. If it's an indefinite integral, which we'll see later when 0 and 1 are not here, then the 83 and 84 can't handle it. At that point, you need a calculator with a computer algebra software built in so that it, I guess you could say, knows some antiderivatives, has them programmed in. But it's a lot more complicated software, so it'll be a little bit more expensive. But some of the TI, like the TI Voyager or Voyage, I can't remember what that one's called, the TI-92, TI-89, and the Inspires, some of the Inspires that have computer algebra software built in, they can do those. But the 83 and 84 can work with these just fine. They're going to get an approximation. So to make this work on your calculator, you have to press the math button. So on the calculator, we would go math, press this button, which is on the far left side of the calculator. And it's the third button down from the top. So you press the math button and then go to number 9. I think it's number 9 on most calculators anyway. But we want this command that says finite integral. We want this command. Now, once you press that command, it depends on your software. Some of you will have software that will have an integral built right in. So when you have that, it's kind of easy to fill in the blanks. But if you don't have that, some of you would just see this. You'll press finite integral number 9, and this comes up on your screen. So if you have this, here's what we have to do. There's some things we need to fill in here. So we have 4 things to fill in. And again, that's if you have this version where it doesn't show a picture. TI-80 or the Texas Instruments calculators have what they call math print, where some of you, when you press this, you'll actually see this come up and there'll be spots to fill these blanks in. So that's real easy. But if you don't have it, the way this command works is you put your function here. This is always x. And you can get that x by pressing the button that says x, t, theta, n. There's a button on your calculator that says this. It is right below the mode button. On the top row of your buttons, it says second, mode, and then delete, the mode button. Right below the mode button is this. You can press that to get this x. And then this is going to be the lower bound and the upper bound. This is the lower bound. This is the upper bound. We have to put these in the right order. In other words, this is the smaller number. So for us, what we would type in here is 0 for a lower bound, 1 for an upper bound. So if I have this version of the software, I would press math and go over to finite integral, and this is what I would type with this version. The function is sine of x squared, so you press sine. This comes up, I press x squared. So I press to get the x. Again, we can just press this key to get the x, and then I square it. And then we have to close a parenthesis. We need to put a comma there. So the comma key is above the 7 key. Put a comma, then I put the x, and to get the x, again, I can just press that. And then we need a comma. And then we need the lower bound, which is 0, the upper bound, which is 1, with a comma in between. And then you close parentheses. Actually, you don't have to close them, but hit enter, and you should get roughly 0.310, I will say 0.31027, I'll say. So some of you had the math print and you didn't have to deal with this. Math print makes it really obvious what you do. You just punch in numbers just like this, and you move around on your cursor keys to get those in there. Either way you go, we should get this number here. Okay, so it's good to know about this command. This command is a nice one to have, and you'll use it all the way through any class that involves calculus. It's nice to know that you can always get a definite integral figured out with your calculator. So now what we're going to do, so of course this is an approximation, it's not exact. There's There is not an exact value here. You'll just get decimal approximations. But we want to come up with a way to approximate it without the calculator. And this is what we'll do right here. We'll use the midpoint rule to do this. And next semester in Calc 2, you'll learn more ways to approximate this, because the sad news is most integrals, if you just randomly make up an integral, there's not going to be what's called a closed form solution. So there's going to be, you're going to have to approximate most integrals that you actually run into in reality. So here's a way to do this. It's kind of an easy way to understand. It's there's kind of a lot of calculations, unfortunately, but we'll do this with the midpoint rule. So what we need to figure out is what is delta x going to be. So delta x is going to be b minus a over n. And b minus a, these are always going to be these, 0 to 1. Remember I mentioned that you have to put these in the correct order in your calculator? So in that previous command, if you had reversed the 0 and 1, whenever you reverse these, you'll find out that you get the same number but the wrong sign. So if in that finite math or finite integral command, if you had reversed the lower and upper bound, you get the same number but the sign is different. So to do b minus a, this is always a down here, this is b up here. So it's going to be b minus a. So it's going to be 1 minus 0 over n, which is 5. They have to give us that, right? We have to know how many of these rectangles are we going to use. We're going to use 5. If we use 10, we'd be more accurate, but we'd also have more calculations. So this ends up being 1/5, or for the decimal fans, 0.2. So if you think about what we're doing, I'm just going to think of a number line here. Let's get this number line. We are going from 0 to 1, right? We're integrating from 0 to 1. So let's go like, I'm going to go by 0.2. So there's 0.2, 0.4, 0.6, 0.8, and there's 1. So we're breaking this up, this integral, or this interval from 0 to 1, we're breaking into 5 parts, right? And this is the gap. So this is delta x. So it's sort of like this sine x squared, this function is up here somewhere. If this is a number line, if you think of this as being the y-axis, the x-axis, this thing would be up here somewhere, and we could find the area under the curve. But we don't really need a picture for it. We are just going to use this midpoint rule, and but I mean, you could draw a picture and you could draw little rectangles in, but what we need to do is find the midpoint. So here are our intervals. We need to find the midpoints, which this one's kind of easy to do. So the midpoints here, we're going to have this midpoint here and along the way. So this midpoint is going to be 0.1, 0.3, 0.5, 0.7, 0.9, right? These are all the midpoints, which we need because we are using the midpoint rule. So we're going to use these midpoints to find the height of, say, this rectangle between 0 and 0.2, right? We're going to use this midpoint. So the midpoint would, geometrically, it would go up. We'd take this, we'd go vertically up until we hit this graph. And when we hit it, we would go straight across. That would be the area of the rectangle we're going to use, right? So we've got the blue endpoints and the red midpoints. So then we can figure this out. So we can say, well, we're looking for this integral, sine of x squared dx. We know that it is approximately equal to the Riemann sum from 1 to 5 of f of x sub I bar delta x. Right, this is just the midpoint rule. We're using the midpoint rule. And x sub I bar, remember x bar is the midpoint, which is all these red points. So what we would do then, we would say, okay, and this thing is equal to, well, we've got our delta x, right? We've got this delta x, and I'm just going to move this out front, just like it does in the midpoint rule in the box above. Instead of plugging in 1 through 5 and multiplying each one of these one at a time by delta x, I'm going to factor out the delta x first. And what is delta x? 0.2, right? Well, actually, I'm going to put this additional step in here. So if we went through here, we would have f of x bar 1 delta x plus f of x sub 2 bar delta x plus, we got to x sub 5 bar delta x, right? So that's what we've got. So we can see then we could factor out this delta x, right? And if we factor out the delta x, we would get delta x times all of these things. So we have this. That's what we would get. And now we can fill in the blanks. So really, we know that delta x is just 0.2, right? We figured that out up here, this delta x. And then f of x sub 1 bar, well, here, each one of these are these red midpoints, right? So this first x sub 1 bar is 0.1. X sub 2 bar, that's the midpoint in the second rectangle. Well, here's the second rectangle. Here's the midpoint. So we go right down the line. So what we get then is, remember, this is a little tedious, but this is what we've got to do. Sine of 0.1 squared plus sine of 0.3 squared plus sine of 0.5 squared. Let's move up here a little bit. So we've got plus sine of 0.7 squared plus sine of 0.9 squared. So one thing to be careful about, let me make a little room here and mention something and put it in red so we are careful. Okay, first we need to be in radian mode. Got to be radian mode because we're punching in sine in our calculator. So first make sure you're in radian mode. I'll put this up here because this wasn't part of my note. But we need to be in radian mode because we're punching in sine in the calculator. Also, here's what I have to be careful about. Sine of 0.1 squared, if I write it like that, that's not what we want because that will be interpreted as the sine of 0.1 squared, which is not what we want. So if you notice inside here, I put sine of 0.1 squared, put that whole thing in parentheses, because if that 2 is out here, we're going to get the wrong answer, right? The calculator interprets this as it's going to do the sine function first and then square the result, which is not what we want. So you have to be careful to do it just like this. And if you do that, you'll get 0.2. I'll write this down. Again, this is just a tedious section. It really is. It's going to be 0.2 times 1.542195404, which is about equal to 0.3084. That's a 0 there. 0.3084. So if you look back at our last answer, with the Cordic algorithm, the calculator uses what's called the Cordic algorithm, but it got 0.31027 is what we put last time. So it's not super close, but we only used 5 rectangles. If we'd have used more rectangles, we would get closer and closer, and we could really get as close as we want just by using more and more rectangles. So remember that when we're doing this, we're doing this midpoint rule. Notice there's no calculus here, right? We're not integrating anything. We're plugging values into this function to get the height of the rectangle, and then we're multiplying by the base of the rectangle. So we didn't do any integration. We're avoiding integration here. We're using the midpoint rule to approximate that integral, which can be interpreted as finding the area under this curve between 0 and 1. Okay, so then we've got some properties of the definite integral we need to know about. Some of these more important than others. I'll point out the ones that are going to be important for us as we go here. But just to mention, if you're trying to find think of this, if you interpret this one as area, what's the area underneath this curve between A and A? It's going to be 0, right? So if you have any integral where the lower endpoint and the upper endpoint are the same, it's going to be 0 every time. This is just a constant. Just to kind of keep in mind, when you see this C, it represents a constant. So this is one I had mentioned before. If you reverse A and B, you get the same thing but a negative sign. So when you reverse the limits of integration, A to B become B to A. It's exactly the same, but a negative. So the magnitude will be the same, but the sign will be the opposite. This is just saying, just like when we integrated and when we differentiated, and I'd say the constant goes along for the ride, same thing here. This constant, we can carry the constant right through the integration. You can't do that with a variable, but you can with a constant. So it's basically saying the C can come out front. It doesn't matter. It's just a constant multiple. If it were being added, we'd have to integrate it, but it's just being multiplied. So the C just goes along for the ride. This one, the integral of a sum is the sum of the integrals. So nothing too shocking with this one or this one. And this one is just saying that if you had, let me draw a picture of this one. So we've got this integral, let's say this is y equals f of x, and we've got a, and then b, and then c. This is just saying the integral from a to b plus the integral from b to c is equal to the integral from a to c. So if you add up this one and this one, it'd be the same as if you just looked at the whole integral, right? You can split them up into two pieces, in other words. And let's see, what else? Number 8. So number 8, it's just saying that number 8 sometimes is used for a really crude approximation. And I used to cover this a little bit more, but I just don't see it as being as important as I thought it was at one point. So remember, calculus, the way it's taught is changing. So they used to be taught with a lot more theory. And it still is sometimes taught that way, where you can't even use calculators in calculus class. But the reality is most students who take calculus are going into an applied field. So it's not really, at least in my opinion and the opinion of many people, it's not as good of an idea to teach so much theory anymore. So we teach a lot more applied problems because most of our students are going into an applied setting. So this is probably where this is sort of dropped off, but it's basically saying, if you look at what it's saying we've got this f of x. So this function f of x is between little m and big M, right? So here's y equals f of x. It's going to be greater than little m, smaller than big M, between a and b. And all it's saying is this integral f of x dx. So the area underneath this curve between a and b, the area underneath this curve. So if we wanted to think of like this area underneath this curve is going to be greater than little m times b minus a. Well, think about what this says. This distance right here, this is b minus a, right? Because if this is 10, if b is 10 and this is 2, you'd say, oh, that distance is 8, right? It's just b minus a. And then you've got this little m right here. So this area right here, that is little m times b minus a, which is right here. So this area here is less than or equal to the area underneath this curve, which we can see is true. And the area underneath this curve is less than or equal to big M times b minus a. Well, big M is right here, right? Here's big M, is this whole distance, where little m is this distance. So big M is this distance. So big M times b minus a, of course, is all of this. So then we can definitely see, yes, it's true that this area underneath here, if we're going to find this area here, it's definitely true that it is between here and here. So, like I said, it's true. It can be used to get a really crude approximation, but it's usually better to use some other approximation technique. So with that in mind, this example 2, I don't really do that one anymore. I haven't done that one in a while. I just need to eventually get that off of the notes. But we will look at one more example here. Evaluating integrals by interpreting them in terms of areas. Okay, so there's a little note. If we're going to do this, we have to agree on something here. And this is what we have to agree on. The note is areas and also length, volume, etc. are always positive. Right? If you ever measured anything on a tape measure and said, oh my God, I got a negative measurement. No, you didn't, right? Length, areas, volumes are always going to be positive. But what we're going to do is we're going to pretend. We will pretend that areas below the x-axis are negative. Why would we do that? Well, if we allow that, if we allow ourselves to pretend that areas below the x-axis are negative, then we can evaluate integrals by interpreting them in terms of areas. If we allow that, we can do it. So, as an example, if this curve goes below here, below the x-axis, then we're going to calculate that area and act like it's a negative number. Then when we combine the two, we'll be able to get this, we'll get the answer to this integral and it will be right. But just to check, let's check this one. See if you remember TI 83, 84. Let's check it with finite integral. All right, so finite integral. If you have the math print, it's easy to type in. If you don't, we're going to have to go 3 minus 2x, comma x, comma -1, comma 3, and you should get 4. Very nice answer. Okay, so I made a little picture here of our situation. So we've got this 3 minus 2x. Think of the line y equals 3 minus 2x. Just a little review from the good old days in algebra. Y equals 3 minus 2x. This is slope-intercept form, right? Slope -2, intercept 3. So it crosses here at 3, then the slope is -2. So you go down 2 over 1, down 2 over 1, and so forth. So this line right here is the graph of y equals 3 minus 2x. And we are interested in the area of this curve between -1 and 3. So here's -1, here's 3. So basically, we've got two areas here. We've got this area here with this. So I'll call this one area 1. This is area 1. And we've got this area 2 right here. Area 2. So remember what we're going to do. To interpret this, to get the correct answer to this by interpreting it in terms of areas, we have to act like this area is a negative area, this is a positive area. So what we can do is this. We can go -1 to 3 of 3 minus 2x dx. And remember, if you've got an integral symbol, we need dx. So the way we can do that is we can interpret it as area 1 plus the negative of area 2. Whatever area 2 is, we're going to give it a negative number. We know that the area of a triangle is 1/2 base times height. So we'll consider the first area base 1 times height 1 plus negative 1/2 base 2 height 2. So to figure this first one out, here's our area 1, base times height. Well, the height is 5, which we can see because if you plug in -1 into here, you get 3 plus 2, which is 5. So we know this point here. Let me label that. So, of course, this line keeps on going, right? This line keeps on going. But this point right here, that point is -1, 5. And also this point right here is the point 3, -3. And we can verify that just by plugging 3 into here. 3 minus 6 will be -3. So then the base here, to find out the base, we need to know that point right there. We need to know that point. Well, we can find that point by just seeing where this line crosses the x-axis. Right? When it crosses the x-axis, y is 0. So you basically solve 3 minus 2x equals 0. Right? Just like in algebra, if you're going to find the x-intercept, you set y equal to 0. So if you set 3 minus 2x equals 0, you'll figure out that x is equal to 3/2. So this point right here is the point 3/2, 0, which means that this base of this triangle is just 3/2 is 1.5 plus another 1 is 2.5 or 5/2, right? So we can figure this is 1/2 times 5/2 times 5, right? The height. Plus -1/2. So we look at this second triangle. The base here, well, if this is 3/2 and this is 3, in other words, this is 1.5 and this is 3, this base is 1.5 or 3/2. So you can put the 3/2 here. And then the height of this triangle, you can see since this is -3, the height of this is 3. So we plug in a 3 here. And if we go through the math here, we're going to get 25 over 4 minus 9 over 4, which is 16 over 4, or 4. So we can interpret the integral in terms of areas if we allow ourselves to call this a negative number. So there's one more thing we need to cover for this section. I'm going to put that on a separate video because I'm going to show you how to calculate an integral without the fundamental theorem of calculus. In other words, we're going to have to actually take one of these limits. So I will do that in the next video. So I will talk to you guys soon.